So what I was telling you was, what is the Hamiltonian of a charged particle? Let me again explain it to you. You need to raise, if at all you have any questions to me. So now, first I told you, a relativist, non-relativistic Hamiltonian has Hamiltonian free particle is equal to, can you see what I am writing?
Yes, ma'am.
Okay. This is free particle Hamiltonian. If I add Hamiltonian of interacting with interaction, I will add p squared by 2m plus some v of r. This is for a free particle. And I told you this is when it is moving within a potential. If the potential binds the particle inside some kind of a given potential, then I will take care of that. That's what is the idea. So now, particle with spin. If you have a particle with spin, then I will write Hamiltonian. I generally say, whenever you have a particle with spin, how do I write it? A particle moving in charged particle. If I have a charged particle moving in an extra electric field, electric and magnetic fields. There is electric and magnetic fields and a charged particle is moving. How do I write this? So I say that wherever you find a P, replace it with P minus QA. P is momentum of a particle minus Q times A. A is the vector potential. How is vector potential related to external electric and magnetic fields is the next question. So you know that given the vector potential, you write what is the electric field. Electric field is given by minus dou A by dou T. I don't remember minus or plus some gradient of some phi, which is vector and scalar potentials. This is a vector potential. Then there is a scalar potential. What is B in terms of a vector and scalar potentials? I want answer. Electric and magnetic fields are related to vector potential and scalar potential. I want you to tell me, how do you write B, magnetic field B, in terms of what is vector potential?
Curl of vector potential.
Curl of A. Okay. And then you also know that there is something called as a Coulomb gauge. That is, if you know, fine. In a Coulomb gauge, phi can be taken to be 0. That is no phi, only A can exist. So then I will get rid of this phi. I will write electric field is given by dou A by dou T. Magnetic field is given by curl of A. When can I do that? I have gauge transformation to assist me. If you change A and phi appropriately, you get the same electric and magnetic fields. I have emphasized it. Choose the freedom of the gauge such that phi can be removed. I will only get everything in terms of A, which doesn't mean that you have only a magnetic field. It is electric and magnetic fields, but by using the freedom that you have of choosing your A and phi with the help of a gauge transformation, I can change it and I will get rid of this A. So now I will say, fine, we have this. I will say that if I have this kind of, what is that I am telling you? I am telling you first a free particle not charged, a free particle which is charged. Then the momentum should be replaced by P minus QA. That's what I should replace, is what our Hamiltonian mechanics tells me. And then Hamiltonian is going to be given by P minus QA dotted with P minus QA divided by 2m. This is the Hamiltonian for a charged particle moving in an external electric magnetic field. Charged particle in an electromagnetic field characterized by electromagnetic field is characterized mathematically by the vector potential. So A of R. From A, you can determine what is the electric field. From A, what is the magnetic field, etc. What I am trying to tell you is there is a Hamiltonian. In the quantum mechanical language, I have to write a Hamiltonian. Fine. Then I also told you, if a particle for a spin half charged particle, what is the Hamiltonian? Hamiltonian is free particle Hamiltonian. Free particle Hamiltonian, no external electric and magnetic field. Suppose there is a spin half, no charge. Particle moving free particle Hamiltonian, that can be written as Hamiltonian is sigma dot P into sigma dot P whole squared. That's what it means, divided by 2m. If I write like this, what is the result? So we have a result called as sigma dot, let us say some alpha, into sigma dot, let us say some beta, where sigma are Pauli matrices. Do you know Pauli matrices? Do you know Pauli matrices? I don't ask you to tell me what are Pauli matrices, but have you heard the name Pauli matrices? Are you sleeping?
Yes.
You have heard. So Pauli matrices have their significance. These Pauli matrices are mathematically, they represent spin. Intrinsic spin is given by half h bar sigma for a spin half particle. That is like how I say momentum is m into v. I say spin, intrinsic spin of a particle has a mathematical structure, that is h bar by 2 into Pauli matrix. Its eigenvalues are going to be plus or minus half h bar. So that is the value I expect when I make a measurement, because eigenvalues of an operator are what you see in an experiment. Any spin half particle has only two values, up and down. So that is coming because you know it fine, but how did it come from? It comes from, if you have a spin operator which has only two eigenvalues, it is called as a spin operator. We derive it. We derive saying that there is a spin operator which is related to Pauli spin operator in the particular way. With that understanding of your knowledge of angular momentum, now I will say, if you take two Pauli operators, that is Pauli operator, and work out what is the product of such an operation. Suppose I take Pauli operator, let us say sigma dot 1 operator. This is a matrix, 2 cross 2 matrix. Matrices, I should say, because Pauli matrix, it's not a vector with an arrow and a direction. It's only a convenience. Otherwise, I have to write sigma x alpha x, sigma y alpha y, sigma z alpha z. Alpha x plus sigma y alpha y plus sigma z alpha z. It should be written like this. In order to condense it, I want to choose a notation. I write a vector notation. There is no vector. Sigma is not a vector. Yes. So Pauli matrix is, I write its components as this, and I say it is a 2 cross 2 matrix which I derive using quantum mechanics. Derived results which you don't remember, I am writing it. After derivation, we have these as our results. They are Hermitian matrices, 1 minus 1. These are the matrices. Then you have done an exercise. If I take Pauli matrix sigma dot alpha, sigma dot beta, where alpha and beta are usual vectors, some vectors. It has a direction and magnitude. Do you know to write what is sigma dot alpha? Do you know to write sigma dot beta and multiply them? That will be the question if I ask you that. So you will write the Pauli matrix sigma x, alpha x. So I have to write a alpha x because Pauli matrix sigma x has components 1 and 1 here. And sigma y has minus I alpha y minus I alpha y. Sorry, plus y, minus and plus here. Sigma z has sigma z into alpha z. I have to multiply alpha z. This is what is sigma dot alpha. Similarly, I can write beta z, beta x minus I beta y, beta x plus I beta y, and beta z with a minus sign here. So this is the explicit form, matrix form of sigma dot alpha into sigma dot beta. You multiply it and express it, you do get the result. That is, result is finally, I am telling you, you should check it yourself. You have done it earlier in second semester. Have you done it? Yes or no? Have you calculated the matrix product sigma dot alpha into sigma dot beta? Alpha and beta are many vectors. I want answer. You know, yes or no?
We have, ma'am.
Huh?
Yes, ma'am, we have.
You have done, but you have forgotten. If you multiply this, result is going to be alpha dot beta. What is alpha dot beta? Explicitly, it is alpha x beta x plus alpha y beta y plus alpha z beta z into identity matrix. What is the identity matrix? It is 1, 0, 0, 1. And plus, I have sigma dot alpha cross beta. So take sigma matrix, dot with sigma x, alpha cross beta, x component. Sigma y, alpha cross beta, y component. It is the result. It's called a matrix identity once you derive it. Once you know it, you have vector identities. What is A dot B cross C? How is it related to B dot A cross C, etc., etc. Same way, once you derive this, it is called a matrix identity. What is the identity here? I have told you, whenever you have Pauli matrices, you have something like sigma dot alpha into sigma dot beta, that is equal to alpha dot beta multiplied by identity matrix plus I sigma dot alpha cross beta. This is a vector, alpha cross beta. So you have sigma dot alpha cross beta. This is the result. Now, where are we? This is a matrix identity. It's a result. Once you derive it, it becomes a result. You can use it anywhere. Now I have to write a Hamiltonian for a particle with spin, no charge. I will write it like this. If I write like this, suppose I write like this, what do you get? Result. You know what is sigma dot alpha into sigma dot beta. What is alpha in this expression? What is alpha? I am checking if you follow or not. What is vector alpha in the square bracket here? I have a relation here. You want to connect it with what I have written. The relation is mathematical. I want to bring it to physics. So here I have sigma dot alpha into sigma dot beta. Instead, I have chosen sigma dot p into sigma dot p. What is alpha here?
P.
Is there alpha? It is p. Beta.
P.
It is p. So now tell me, what is this identity here? I into, tell me, I into alpha dot beta.
P square.
P square. Divided by 2m is there. I will write. Plus next term.
0.
0. So I get Hamiltonian is nothing but p squared by 2m multiplied by an identity matrix. That is, because spin is there, you do get it two different particles are there. Two levels are there, spin up and spin down. But the whatever is the Hamiltonian for a free particle with spin half, this is the Hamiltonian. Then I will move ahead, and if a charged particle is moving with spin half in an external electric and magnetic field in a Coulomb gauge, that is A is there, no phi is there, I can choose it as per my wish by choosing the gauge. That is, which is easier for me, I will take it. That's what I mean. So I will write a Hamiltonian of a charged particle with spin half in an electromagnetic field. Now, first thing I should notice is this is a non-relativistic expression. I am writing a non-relativistic Hamiltonian. So non-charged, non-relativistic particle with spin half in an external electric and magnetic field is given by, I will say, sigma dot P minus QA into, I will write a whole square divided by 2m, because P has to be replaced by P minus QA by QA. That's what I told you. That is, Hamiltonian dynamics tells you what is a momentum. Momentum, generalized momentum for a particle in an external electric and magnetic field is given by P minus QA. That's what I will say. So in that case, I will tell you that this has to be simplified. It is not easy to simplify. You have already done this in your Dirac equation. That is, how does it work? See, when you don't know how to solve it, you think that somebody is fooling you. No. If you work out, you will get it. That much of confidence you should have. If you don't know to work it out, you have to learn to work it out. Or at this point of time, you are not asked to work it out for your exam, but you should know. So I will just show you what is that I am talking about. So I have a Hamiltonian, which is 1 by 2m sigma dot P minus EA by EA whole square. That is for a proton. Q is what for a proton? Q is equal to E. That is, charge of a proton is plus E. So I am writing that. Plus the proton is also moving in a nuclear potential V of R. I am writing that part. So A denotes the vector potential of the electric field. And in the Coulomb gauge, I have already explained how you write your examination. This is all you write. All other things, you know it already, so you don't have to write. A denotes the vector potential of the electromagnetic field in the Coulomb gauge. That means electric field is given by minus dou A by dou T, and B is given by curl A. And A of RT for a fixed energy radiation, this is e to the minus I omega t time dependent. That continues. If you have a fixed energy electric and magnetic fields, A of RT also has this kind of a time dependence. Time dependence is common. Then, if I simplify equation 1, this one, you should learn to do it. I don't want to say how to do it. You have already done it in Dirac equation class. I am not going to explain it again to you. What is P for a quantum mechanical particle? I will just ask you. What is P of a quantum mechanical particle? Can you tell me what is P? Momentum of a quantum mechanical particle. Do you know how to write mathematically what is momentum of a quantum mechanical particle? I want yes or no. Okay, not P. I will ask you what is Px of a quantum mechanical particle. In quantum mechanics, how do you write Px?
Ith cross d by dx.
Yes. This is what is P. So you should remember that it's an operator and A is a function. Vector potential is a function of XYZ. So if you write a P minus EA into P minus EA, you will get a P squared. It is dot product, whole squared if you do. There is a P squared P dot P, I write it as P squared, and P acting on A, that is minus E, P dot A minus E, A dot P, that will come. So here P is an operator, it operates on A as a function of R. But A here is left hand side, P, all this has to operate on a wave function. So this P only operates on a wave function. So I have to do such clear thinking when I simplify it. I am not going to do it because these are all done to you in your second semester. I will only appeal to your understanding. If I simplify, I obtain the interaction Hamiltonian. After I simplify, I will tell you what I get. I will get Hamiltonian is P minus EA dotted with P minus EA. Oh, sorry, sigma dot P minus EA whole squared divided by 2m plus V of R. That is our potential, that is our Hamiltonian of a proton, which is moving in a potential V of R with its electromagnetic field. There is an influence of an electromagnetic field also, in addition to the nuclear binding. So if I have this, I will say this Hamiltonian, I have to simplify all this. I will write finally simplified Hamiltonian as P squared by 2m plus into I, that is 2 cross 2 identity matrix, P squared by 2m plus V of R potential plus a H interaction. What is that H interaction can be written. It can be simplified, and this H interaction is a 2 cross 2 matrix Hamiltonian because it's a spin-off particle. Don't get confused. You should know free particle. You can write a operator. If you have a spin particle, it's a matrix Hamiltonian. Each matrix element will contain a differential operator like potential, momentum, etc. So don't worry about it. You have learned it in your Dirac algebra, Dirac equation class. So I am only telling you what will appear after a interaction. So I get H interaction is equal to minus E divided by M into P dot A. P is momentum, that is minus IH bar del kind of an operator, dotted with what is the external that is electric vector potential minus EH bar by 2m into sigma dot P. That's what you obtain when you simplify your equation, what I wrote here. That is this quantity. You have to carefully simplify it by noting that the P is a dou by dou x operator. It operates on A as well as on some psi also, because Hamiltonian has to act on a wave function. So this operator Hamiltonian, I have to take care of what depends on XYZ, what depends on wave function XYZ, etc. So with so much of care, I write your interaction Hamiltonian. I will write it again for you to register it in your head. Interaction Hamiltonian is given by P dot A, I think there is a E, plus I have sigma dot B EH bar divided by MC. I think so. I will check it because I don't remember. How to remember, I will tell you. EH bar by 2m. Sorry, this is what I have. And then this is E by M. Fine. So I have to write this. I have corrected it here. So this is something which looks like what you had done in your earlier, that is, if you know, do you know how a magnet interacts with another magnet? So basically we say a magnet interacts with another magnet through this kind of an interaction where this is a magnetic dipole moment. I'm telling you several things which are all needed for you to connect with each other, connect with one concept to another. I am only talking to you after simplification in the class. But I also want you to connect with a concept. When you put two magnets, you know that they get attracted or repelled depending on whether I have a south pole, north pole aligned properly. How do I write it mathematically? I say that a magnet has a dipole moment, another magnet has a dipole moment, they interact with each other. And then I also know that magnetic dipole has its origin in angular momentum. I told you that. Do you remember what I told you in your class? Magnetic dipole has its origin in the angular momentum. I will try to tell you some other time how one realizes that magnetic dipole, property of magnet comes because of the orbital angular momentum and intrinsic spin angular momentum of the particle. So if I check it, I realize that this mu1 and mu2, mu1 is proportional to, let us say, angular momentum L. It is proportional to means there is a constant which comes with it. Mu2, I will call it as L1, proportional to L2. Then mu1 dot mu2, that is interaction energy or interaction potential. Potential energy. Free particle moving, kinetic energy is one thing. Because of interaction, you have a interaction potential. That is mu1 dot mu2, and that is nothing but it is proportional to angular momentum dot product L1 dot L2. So now I will say, if you have a particle which has angular momentum, orbital angular momentum L and spin angular momentum S, then you do have L dot S denotes the spin orbit kind of a interaction. This is called spin orbit coupling. That's a magnetic interaction, coupling. Because you have a spin particle with spin, there are two different types of magnetic moments. One is orbital magnetic moment, one is spin magnetic moment. So you have spin orbit coupling. Now, if you say, this is one thing. If you say, I have another thing, what do I have? I have a particle with spin and there is an external magnetic field, electric and magnetic field. How do I write spin half h bar? So how do I write interaction of a particle with an external magnetic field? My interaction Hamiltonian should have L dotted with B. B is the magnetic moment plus S dotted with B. That is, there is an overall factor. That's any magnetic interaction. You have two magnets. Now, spin of the particle interacting with a orbital angular momentum is one type of interaction. If you have an external electromagnetic field, interaction is written like this. I am educating you. So you have L dot B term, S dot B term. So that is our Hamiltonian of a charge interaction Hamiltonian for a particle. Now I will say this has a factor, this has a factor. This interaction has to have units of energy, magnetic momentum, that is interaction. So I will say that this is EH bar divided by M L dot B plus, here I get EH bar divided, 1 minute, M 2M into sigma dot B, because S is nothing but H bar divided by 2M. There is a constant multiplying it. So I will say that I have this quantity is the magnetic moment, EH bar L by M. That's the magnetic moment of a charged particle coming because of its orbital angular momentum. So L dot B gives you magnetic interaction of orbital angular momentum. Spin dot B gives you intrinsic spin also interact with the magnetic field. You have these two terms. You can check carefully that this term would reduce to what I have written there as P dot A. It can be simplified. I can write this as E by M into P dot A. If I explicitly write what is P, P is gradient, that is minus IH bar del operator. So I have to substitute all that, and then I will get this is reduced to this particular quantity. So then I notice that the Pauli operator, this part, has some particular factor. All these are known to you from Dirac equation. If you have done Dirac equation, you have learned that how a charged particle moves in an external electromagnetic field and how does it appear in the non-relativistic limit. So I get Hamiltonian, interaction Hamiltonian given by spin interaction part, that is magnetic moment due to spin dotted with B, mu dot B, spin part, mu dot B. Again, if I simplify it, you will know. I don't simplify it for you. This is L dot B into S dot B. But we notice that L dot B term has a coefficient EH bar by 2m, etc. And I have a S dot B. This appears twice. That is spin contribution when it interacts with the external magnetic field is double compared to what is this orbital angular momentum contribution. This is a realization. I am not telling you. When we do mathematics, I find that spin contributes twice to that of orbital angular momentum. So we cannot ignore spin part. Spin part acts strongly in the external magnetic field is what we realize. So with that, I will come back. Our aim is to know what is the interaction Hamiltonian, and I got this interaction Hamiltonian. All that what I was telling you was to make you familiar with what is the energy of interaction when I have a charged particle moving in an external magnetic field. A charged particle with spin is like a magnet. A magnet-magnet interaction is mu1 dot mu2. So mu2, one is a magnetic field, one is a charged particle. So charged particle has two parts. One is orbital angular momentum part, one is a spin angular momentum part. That's what is condensed mathematically in your equation 2. I hope you understand. Now, what is it that I want to do? My aim here is to find what are, say, something like AELM, AMLM in the quantum case. Earlier, I had done everything in classical case. In the quantum mechanical example, what are these coefficients? Can I determine what is the electric field and how do I write the coefficient of a particular multipole type, electric type, magnetic type, all that, will it appear? So what I have to do now is to work out, not doing explicit work, I will say a transition probability T from state A to state B is given by Fermi-Golden rule, and that is 2 pi, what is called as density of states. That is quantum mechanically, you have several states decaying. I don't want to go into that muck because you will get confused. So this is a factor which comes from your Fermi-Golden rule, and then pi b, lambda b, h in pi a. Now tell me what I have written here. Is it an operator or is it a number? What I have written here, I am showing it to you here. This quantity. Okay, I will ask you 2 pi. Is it a number or is it an operator? H bar, is it a number or is it an operator? I will keep asking until you answer. H bar, is it a number or is it an operator?
Number.
It's a number. It's called Planck's constant. It has a value, correct? 2 pi, 2 into 3.14, that's a number. Rho of E is density of states, which I give you number. So now, what is phi A? It's a quantum mechanical state vector. H int is an operator. An operator acting on a state gives you another state. And then when you take an inner product with this state, inner product of two quantum mechanical states gives you a complex number. Mod squared of a complex number gives you a real quantity. And transition probability is such a number. If you do this whole exercise, you get some number which lies between 0 and 1. It's a probability. So I get this kind of a expression. I'm not telling you how you got it. You've done it in your time dependent perturbation theory. But this tells you, if I have what is called as a two-level system, say I have phi A, then I have a phi B. I want to know if a transition particle existing here makes a transition from A to B. What is the transition probability that A state particle goes from A to B? So in a hydrogen atom, particle is in an excited state, it comes down to a ground state. What is the probability of finding it? Is if you ask such a question, I will say phi A to phi B transition probability is given by, do you know the interaction? Yes, I know the interaction Hamiltonian operator. I will write a phi A, I will write a phi B, take a mod squared, this is a real number, and then I multiply it with what is called as 2 pi rho by h bar. This is what I say is the transition probability. If this transition probability is 60%, that is 0.6, then I will say there is a 60% chance. If you take 100 such states, A and B, 60 times it will decay into from A to B, make a transition from A to B is what I will say. If it is, let us say 0.3, it's only 30% of the times. That is, if you take 100 such two-level systems, how many times it goes from A to B? It is 30%. That's how we talk about transition probability. There is a transition. If you want to recall again, I cannot simplify what is phi A. Is it a EA times phi A? No, I don't have such facility because Hamiltonian is time dependent. I cannot do all that. I do perturbation theory. From first order perturbation theory, this is the expression for finding probability of a particle making a transition, quantum mechanical particle making a transition from any initial state to any final state. I have a facility to calculate it if I know how to operate etching on your initial state and then take an inner product. All these are calculations. We know to do it. You don't have to do it now. If I do that, I will say substitute what is etching. You know that etching is given by this particular part, and A is nothing but E is equal to minus dou A by dou T, or A, if I substitute A is A for e to the power minus I omega T, I get this expression. Once I simplify this, write what is E is I omega A, or A is E by I omega, substitute E and B in terms of the multipole expansion and identify what is the transition probability for going from A to B. What is the transition probability? Your Hin contains the external electric field and magnetic field. Electric field can always be written. It's a classical electric and magnetic field. I can write it in terms of multipole expansion. We know it already. If I substitute it and check rest of the part, writing all that and taking an inner product of phi A with phi B, if I do all that, what is the result that I get is written in a long expression. You have to have patience with me. I'm only telling you a story, not making you work out details. Once I write this, that is what am I doing here? Step number 1, substitute what is Hint. Hint is nothing but all this. Now in this, you substitute what is A. A is given by E divided by I omega. And I also simplify B. Instead of A, wherever curl A is there, I will substitute B in the H interaction, Hamiltonian. I substitute it and then I simplify it. When I substitute electric field, whenever I write an electric field, it can always be written in terms of the external, that is multipole type fields. That is what we have learned already. I'm only doing quantum mechanical things, but electric and magnetic fields are something, radiation, which I see in my lab. So it is a classical thing. I write this in terms of coefficients here. Then I obtain, simplify what is, after substituting this in terms of E and B and multiple expansion, and then simplify this. What I obtain is the only thing that I'm going to tell you. Once I simplify this, I get TELM, that is the transition probability. I don't call it anymore by AELM. I will drop AELM, keep it preserved for classical. If I come to quantum, I will say there is a transition probability, TELM and TEMLM, and I will tell you how does it work. So I will say TELM, TELM is AELM mod square. I made a mistake of telling you something, forget it. So TELM is transition probability. It is nothing but AELM mod squared. How do you get it? If you only simplify, only if you simplify the transition probability expression and check it, you will get similar expression what I had shown you in the case of source dependent Maxwell's equations when you have a classical charge distribution emitting a radiation. See, we are going step by step. First step, what I did is to tell you electric and magnetic field for source free region. All are fixed energy. Source free region. This gave you what is called as a multipole expansion of external, whatever is there. Any electric and magnetic field should be written in terms of multipole expansion. But then I will ask, what are the coefficients? How do I write it? So I have to talk this in the source region. That means I have to take most general Maxwell's equation, classical source. Here I will write classical source. Any charge distribution, current distribution, that gives you a magnetic field, as you know. So what is the electromagnetic field? I derived what is AELM, AMLM in terms of source properties. Okay, I have it in terms of the source properties. Now I come to quantum mechanics. I am writing a transition probability of getting a radiation with specific L value, M value, which is electric type or magnetic type. This is equal to AELM mod squared is what I will define. That is a definition that I know it. I will write it. And then I will say this quantity is given by L plus 1 divided by L into 2L plus 1 double factorial whole squared, and K is the wave number, K to the power 2L plus 1 divided by H bar, and QLM plus QLM prime mod squared. If you recall what we had obtained in the case of our, where is it? Just a minute. Here. We had also worked out in the case of classical particles, classical charge distribution, AELM was something like this. What is AELM mod squared? You may work out. Then you get QLM plus Q prime LM mod squared is what you get. And check what is QLM. QLM is written in terms of classical charge density. Please be with me. Take particular attention that charge density appears here. Then there is a YLM. I had shown you explicitly L is equal to 1 case gives you dipole moment, etc. So this was earlier expression. Now we are looking at a quantum mechanical expression. This is QLM. It looks like QLM. What is QLM? It's not the same QLM. It depends on the source. What is our source now? When I am talking about quantum mechanics, what is our source? What do you mean by source? I have repeated it, but do you understand what I am saying? What is source emitting a radiation? In the case of what I am talking about, quantum mechanics. What is source in classical theory? and what is source in quantum theory that I am talking about? I want you to tell me that. What emits a radiation is called source. Okay. In the classical case, what is emitting a radiation? Are you there with me or sleeping? At least you can say, we don't know. I don't know. How many say don't know? I will record. What is meant by source? In classical, source means I am talking only about your understanding. What is, I use a word source. What do you mean by that? Source is
charge density.
Charge distribution. If you have a charge, classical charge distribution, that is called a source of radiation. In quantum mechanics that I am talking to you, what is source? In the particular situation that I am talking about, where is a source? What is the origin of radiation coming out?
Wave function.
Proton, let us say.
Proton.
And proton, in the case of gamma decay, proton is a charged particle, and proton has its wave function. So I don't have a rho of r, but I have what is called as a proton wave function, which will give me what is called as charge density. For example, I will tell you that if you have, let us say, phi b of r star phi a of r d cubed r. This is what gives you what is the transition from A to B. This is what is kind of related to rho of r. Classically, what is rho of r gets replaced by the wave function of a charged particle. So I will say a particle makes a transition from A to B, associated charge density, concept of charge density, that is given by a corresponding expression, which I will show you now. QLM is nothing but, it is QLM comes because there is a state, there is a B wave function, A, B star here, and R to the power L, YLM star theta. Let us stare at this. I will write it down and tell you what I have in the classical case, what I have in the quantum case. I am writing QLM. I am writing it is because A to B transition is there, and I will write D cubed R, R to the L, YLM star theta phi, and phi B star of R, phi A of R. I will go there and show you what I have written. This is what is, okay, I will write this. QAB LM is what I had in my notes is what I am writing. This appears when you simplify, you get it. You are not simplifying. So you have to believe me that when you simplify, you are going to get this as your QLM. That is what I am talking about. Some coded quantity called QLM. This is what you have. What was it in the case of classical thing? QLM. QLM is going to be, there is no A and B. It is simply related to YLM star of theta phi and rho of r. I will go there and compare both the cases. I have rho of r. This is what is the classical expression. This is quantum. Quantum needs a different language. I have a state A characterized by a wave function phi A, characterized, this is characterized by phi B. Will it make a transition and emits a radiation? Yes, it does, depending on what is the value of QLM. Phi A, there is phi A, phi B, and same things here. So what I have written, there is a charge here. I forgot to write a charge, I think, in the earlier expression. Where is this? There should be Rho of r contains a charge here. Rho of r means charge density. Rho of r, integral rho of r is charge basically. But here I have it in terms of what is called as, I have written here, 1 minute here and here. This Q, can you compare what is rho of r in classical case? What is it replaced by in the other expression? There is a QLM. There is a QLM. This is classical. This is quantum. So what is the difference in the two expressions? I should replace rho of r by what is called as E and say integral d cubed r. Oh no, E into phi b star of r into phi a of r. That's what gives me what is called as charge density. That is rho of r, it should be replaced by this. There is a language for us in terms of the wave function, which we have to write. Then I get a description of what is quadrupole moment, what is a magnetic dipole moment, what is a electric dipole moment in quantum mechanics. So once I extend my understanding, like how you say, momentum is m into v, classical. But when I come to quantum, it's an operator. And this operator is written as minus IH bar del. Like that, I have to recognize what is rho of r, what is the associated charge density in quantum mechanics. Once I do that, I do have recognition. Oh, this is the same. It looks the same because QTELM depends on what is the quadrupole moment, dipole moment, etc. So I write this, and these are the expressions. You don't have to, that is, if you remember, fine, but otherwise you have to kind of write it similar to what is classical, where the charge density and current density and all that are replaced by their appropriate quantities. So for the special case of dipole radiation, in which case L is equal to 1 and M is equal to 0, like how I did, this is not seen very clean. Phi 0, 10 AB is E into root of 3 by 4 pi d cubed r phi b star z phi a. So that is a dipole moment. If you take dipole moment, I will tell you again what is a dipole moment in quantum mechanics. So let me say dipole moment, classical. I have to be careful, electric dipole. If it is magnetic, there is a difference. Electric dipole moment, I had told you, it's a vector D notation, and I write charge is E, let us say charge is E, and then there is a position of the particle. This is what denotes if you have two charges, one is plus E, one is minus E, distance between them is a vector R. It is denoted by vector R. I had written this earlier. This is 0, R1, R2, R is R1 minus R2. Let us say. So that is what I told you is the electric dipole moment. What is quantum? Dipole moment is measured experimentally. It should be a number. How do you get that number? I will say the dipole moment is basically given by E d cubed r. There is a space, and then I have a wave function phi star r and phi. Let us say B and A here. Phi B, phi A, and R. What is Z component of the dipole moment? I will say it is d cubed r phi B star of R and Z phi A of R. Do you follow what I am saying? I am only teaching you what is the quantum mechanical analog of dipole moment. And then I will say, do you see it here? Q10 is phi B star Z phi A. It's one component. L, M. M is varying from -1, 0, +1. 3 components for a dipole moment. And I write Z comes as the moment. This is the Z component of the dipole moment. Same way I write M10. You will be surprised to see it is LZ, angular momentum, magnetic dipole moment, comes from the angular momentum. So I do write this, and Q prime, it depends on spin part of it. Q prime is a charged dipole moment, also comes from spin. That's what is written here. It just comes, you should be able to appreciate what is the origin of it. And M10 prime is the spin magnet dipole moment. So these are the expressions that I get for what is called as transition probabilities. Transition probabilities depend on QLM, QLM prime, MLM, and MLM prime. For different values of L and M, I can evaluate, I can work out what is the transition probability. Once I do that, I will say, fine, I have got these things, and it is only for single particle, single proton moving in a nucleus emits this radiation. How do I do when I have several protons inside a nucleus? Generalization to systems containing several protons is obtained by summing over single particle transition over all the protons in the nucleus. It looks complicated, but I will tell you how one can identify. Many cases, we are not able to calculate things explicitly. That is, we cannot explicitly write the number, but at least I get an idea. What is it? So I need to know how does it appear. Once I know how it appears, I can make some predictions, if not explicit value of the whatever I am going to get. So this is what is the thing as of now. I want to tell you more about gamma decay later. Right now, what I know is just. So I have talked to you about a particle. Suppose I have charged particle E and B. For a definite energy, they need multipole value. They have a multipole value called as L and M, and electric type and magnetic type. These are something that you should know. Electric and magnetic fields should be written in terms of their multipole value. What is the multipole value of an electric field? What is the magnetic value, that is a multipole value of a magnetic field? Are the fields electric type or magnetic type? That you should get familiar first. So electric and magnetic fields are classical, fine. But now my source is quantum. In the case of a quantum source, I know what is a transition probability, which gives me what is the electric field emitted here, how much of electric field, electric type, which has multipole value L and M, emitted when a nucleus makes a transition from state A to state B. That is transition probability. Our language is about transition probability, and this transition probability depends on what kind of states I have. That means what is the charge density rho of R or current density J of R. That is what is contained in these wave functions and all that. So I will be able to calculate this, and I will be able to say, tell you finally what I call as, suppose I have a radiation here. This is, let us say A. Here, let us say I have a B. I make a transition and I get a radiation. So if I have a radiation, what characterizes it? I will tell you now. Gamma is characterized by energy, multipole value L, M, and electric or magnetic type. All this is now understood. I started with this as selection rule. Now I have come to a point. If you can calculate the transition probability and say, if transition probability is not 0, then you will say there is a radiation with particular L value, with particular M value, and with a definite energy. It is electric type or magnetic type. I can talk about all those things because all this is contained in a detailed calculation, which I didn't do and I didn't show you, but people who did it, they get all these kind of characterizations of a gamma. That is fine. Okay. So now how do I experimentally determine what is L value, what is M value? If I only get a gamma ray, I have a detector. Okay, that's what is the next story, which I will not do today. Because you have I know you have a 2-hour class today, but it is little heavy. So I will take one more. Next time I will talk to you about how to determine experimentally. I only have a gamma ray. A gamma ray I don't see. I have a detector. Let us say a single channel analyzer is there. It detects a gamma. Can I know with the help of a single channel analyzer, what is the L value, what is the M value? That is what is called, what I call as angular distribution studies. Any radiation is coming, what I need to do is to check. Radiation means electromagnetic radiation. If I have a radiation coming, it is not coming in one direction. It is coming in all directions. Why? Because my source emits several radiations per second. Per minute, I have, if you have a source of gamma particle, it has so many nuclei, it emits gamma particles, and gamma is distributed everywhere. I keep a detector here and check how many particles are coming, number of particles. And then one n theta is the number of gamma particles, let us say. So then I will say, if there is no difference, if I check, keep the detector, change the detector by some angle and detect, is it's same, theta prime gamma is equal to n theta gamma, then I will say the distribution is isotropic. There is no change of gamma particle coming in different directions. But if it depends on, this is not equal to this, there is an angular distribution. Don't get mixed up with when I say isotropy and all that. I was talking about in isotropy of space and all that. This is a different concept. Now I am talking about nucleus emits a gamma particle. Are the gamma particles emitted in all directions? Are the number same or is the number different? That number is not same, and it depends on the L value is what I will tell you next. If depending on the value of L, multiple value, you will find that if you check the number of particles as a function of theta, you will not find a straight line. That is, it doesn't depend on theta. No, it depends on theta. There is some particular pattern of this. That pattern is a signature of L. If L is 1, there is a typical signature. L is 2, there is a typical signature. That's what we are going to learn in the next class. It is called angular distribution studies. So that is in the next class. So I will stop sharing the screen. So now, if you have understood, you have to think about it. I will share my lecture notes. But if you have any doubts, please message me. No problem. If you want to ask me anything now, you may ask me. I will keep it for 2 to 3 minutes. If you have any questions, you can ask me. Otherwise, you may keep going on. That is, you can go out from this.